In this video, we'll use the VPADD instruction to do packed addition. In the program here, I have two integer arrays, array 1 and array 2. Each of these arrays has 8 elements, and our objective is to add each element in array 1 with the corresponding element in array 2 and store the result in the result array. So we'll use the VPADD instruction to accomplish this. Before we get into the coding part, let's quickly look at the layout of these arrays in memory so that we can better appreciate how the packed addition operation is being performed. So a packed d-word integer is just a sequence of d-words which represent more than one integer values. So here, if you look at the layout of array 1, we see that it's got 8 elements, and since each of these elements is an integer, they occupy 4 bytes in memory. So 4 bytes for each element, and 8 elements evaluates to 32 bytes. So the total memory occupied by array 1 is 32 bytes. And you can see that array 2 is also occupying 32 bytes in memory. So the idea here is, when we use packed addition, the CPU is going to add the element in array 1 with the corresponding element in array 2, and it's going to save the result into a temporary register, into an XMM register, from where we will move it to the result array. So at the end of the program, we expect our result array to contain the sum of the individual elements of array 1 and array 2. So let's look at the sequence of instructions we are going to be using. So the first instruction we are going to use is the vMoveDQU instruction, and this instruction merely loads 128 bits, which is the 16 bytes, which is the first 4 elements of array 1. We'll load that into an XMM register. Then we will do the packed addition of the values that are loaded by the previous instruction and the first 4 elements of array 2. So when we add these two, we save that to another temporary XMM register, and we move, in the third instruction, we move the saved result into the result array. So this sequence clearly shows that we are only performing 128 bits of addition, and as I said before, these arrays occupy 32 bytes, which means that only 4 elements are being processed. So the solution for us is to repeat the sequence of these 3 instructions for the next 4 elements for the result of the addition to be complete. So what we'll do is repeat these 3 instructions again for the upper 4 elements, and as before, we will save the result into the result array. So at the end of the program, the result array should be populated with the values which reflect the addition of the corresponding elements in array 1 and array 2. So let's go back to the program here, and let's start with our input and output list. So for our input list, we know that the input list will come from array 1, and we'll use the memory constraint for that, and the next input is going to be obviously array 2, and with the same memory constraint used here. Now as I said before, we are going to repeat the sequence of instructions for the upper 4 elements. So when we repeat that, we want to add 2 more inputs, and in this case for the second time around we are going to want the upper 4 elements of the array. And likewise for the output, we know our output will reside in the result array. The first time around it's going to reside in the lower half of the result array, and the second time around we are going to put the result in the upper half of the array. So once we have the input and the output list complete, let's just start coding the sequence of instructions we saw in the lecture. So the first instruction that we are going to use is vMoveDQU to load the first array, and you can see that the destination is an XMM register and the source is the memory location of the first array. So we'll use the vMoveDQU instruction, and the source is the first array. So here is our first array, and the way I refer to it by using a placeholder is as follows. So the first element here in the input output list is %0. This one would be %1. So array 1 of 0 would be %2. So we use the placeholder 2 here, and I want to move this to an XMM register, and it does not matter what XMM register I use as long as I keep it consistent here. So I'll use the XMM1 register here, and once I have loaded that, then I can use the VPADDD word instruction. So going back to the specification here, VPADD, the destination is an XMM register, the source is the XMM register into which the first array got loaded to, and the second source which we are going to use is the other array, which is array 2 in this case. So I'll use the array 2, and by using the placeholders, array 2 is denoted by %3 here, and I want to add array 2 with array 1, which was loaded in XMM1, so I want to keep that consistent here, so I use the same register. So once I have added these two, I want the destination register to go. Destination register can be any other XMM register, so I'll use XMM0 in this case. So now that the addition is done, the only thing that remains to be done is to move the value from the result into the result array. So the result is in the XMM register XMM0, and I want to move that to the result array, and that's denoted by this placeholder %0. So I've done the first half of the array. So the first 4 elements of the array have been processed, they've been added, and the result has also been updated for the first 4 elements. Now for the next 4 elements, the process is fairly simple. I just copy these the sequence of these 3 instructions. We are going to do the same thing, except that the values that we are going to load is different. So for the first part of the processing, we loaded array 1, so which the first 16 bytes of array 1. Now we are going to load the next 16 bytes of array 1. So that, to refer to that, we'll use the placeholder %0, %1, %2, %3, and %4. So that's the placeholder we are going to use, and for the addition to be performed, we want the upper 16 bytes of array 2, so that can be denoted by this placeholder %5, and the final result, when it is saved, I will use %1 for the upper 16 bytes of the result array. So now that I'm done with this, I just need to build the program and verify that it's giving the results that I expect. And the one other thing I wanted to quickly mention was, if you have a CPU that supports AVX2, you could replace all of these instructions with the 256-bit version of the instructions that AVX2 provides, and in that case you will not have to repeat this process 2 times. You can just do the entire addition of these 256 bits with the sequence of just 3 instructions, and those 3 instructions will operate on 256-bit values as opposed to the 128-bit values that I'm using here. But for that you will need a CPU that supports AVX2. So now that we are done with this, we'll just build this program and run it, and I get an error here which is probably due to this additional comma here. And let's see, and it builds, and let me run it, and you can see that as the code iterates through the result array, it gives me a result which is consistent with my expectations. Each element of array 1 has been added to the corresponding element in array 2, and we see those results displayed in the result array.